Okay. So, hello everyone. Welcome to this Applied Mechanics Seminar Series, and it is my pleasure to welcome Professor Ravindra Duddu from Vanderbilt University. So, Professor Ravindra Duddu is an expert in computational solid mechanics. I'm particularly myself a fan of his work on glacier and fracture modeling in glaciers. He did his PhD and masters from Northwestern University. He did 2 postdocs from Columbia and UT Austin, and a bachelor's from IIT Madras. And he is recipient of a number of awards, including the Kalam Fulbright Award, where I think last year you were visiting India, right? The Royal Society Exchange Program and of the NSF Career Award. And he will be giving a talk on CNNs and cell-based MLPs for solving fracture and multi-scale elliptic PDEs. With that very brief introduction, welcome to the department, and we are really excited to listen to you. Thank you.
Thank you, Shoaib. Thanks everyone for joining, and it's really high praise that coming out of you that you're a fan of my work. So thank you for that. That's really high praise. And yeah, on a very chilly but wonderful day like today, it's a happy day to visit IIT Delhi again. So normally I would come here and make a presentation about phase field fracture, cohesive zone models, XFEM, and level sets. If you know any of those terms, what those mean, that's sort of my comfort zone. But today I'm going to dare, and I'm going to step out of my comfort zone a little bit and talk about machine learning and neural networks and what we learned through this one project that my PhD student did with funding from 3M of all places. And hopefully this will be a chance for you to ask me questions, for me to learn more than what I learned through this exercise, and perhaps you will learn some too. And it's a mouthful, but I'll break it down what my title is in the next slides. So moving forward, as I said, my group is called Computational Physics and Mechanics Lab. And when I first moved to Vanderbilt under the Civil and Environmental Engineering department, my ex-chair asked me, "There's no engineering in your lab. So how do you expect to get tenure in the engineering department?" So, but still, I think every engineering research is founded and has a foundation on physics and mechanics, especially in this department, which is called the Department of Applied Mechanics. I would fit right in. Right? There's no issue here. So broadly, I established my goals as predicting material degradation, and so fracture, corrosion, and those involve mechanical, thermal, chemical phenomena. It's interdisciplinary research, and I mainly focus on this mathematical and computational modeling. Right? And you can set up advanced models to do science, or you could focus more on developing methods and get into the mathematics of how do you do numerical methods and how do you approximate functions and so forth. And there are a lot of focus areas in terms of applications. As you know, in the US, it's all funding driven. So a lot of my funding came from NSF, or that focused on Antarctic ice shelves, from ONR, that's related to laminated composites and woven composites. Recently, we've been working on rock materials, sort of in the geothermal energy space. So we are looking at fracture in that space. But overall, we focused on how to develop better models and methods to simulate fracture. But on to a lesser extent, we also looked at interface evolution. So corrosion, which is a type of material degradation, involves interfaces dissolving. When you have metals under high temperature, they form second phase precipitates. So that's a type of interface evolution. When you deform a hydrogel with extreme deformations, then you also need to track those deformations, and traditional Lagrangian methods don't do very well. So we formulated Eulerian methods, and then we have interface tracking there. And also recently we were looking at cliff failure, sort of when you have rock cliffs fail and then you have natural hazards. And we've been using MPM for that. So that's sort of my comfort zone. I wanted to define that before I move into the not so comfortable zone. And before I do that, I want to acknowledge my collaborators, Matt Berger and Sohail Kalouri, who are computer scientists, who kind of pushed me into this when we got group funding from 3M. And then we had some funding from NASA to also do machine learning. So I'll come to the ice flow problems a little bit later. And of course, all the work that I'm presenting is from the PhD thesis of Yuxiang Gao, my brilliant PhD student who now is working for a dental company which makes implants, dental implants, and he's using machine learning to design patient-specific dental implants. So the point I wanted to mention is that when you do mechanics and these data-driven new approaches, you can also apply them in industry as well. So academia is not the only path for PhD students in this regard. Okay, and Abhinav is a postdoc who helped with some of the phase field simulations in this. So background, as I said, I focus on fracture, material modeling. So we always thought that characterization of heterogeneous materials is our goal. And you have carbon fiber composites, you have particle reinforced, you have poroelastic materials. And of course, 3D printing makes it easy for us to create these materials in the lab. But modeling and simulation is harder because you have to now account for the heterogeneity at different length scales. And that means that your traditional finite element methods are not always going to be so computationally feasible, right? So imagine if you had to resolve at the scale of this fiber reinforced matrix, you have to resolve each and every fiber and then model it at the scale of a component. It would be prohibitively expensive, right? And so you have multi-scale methodologies. A lot of work has gone into those sort of things, but machine learning is somewhat motivated, or the research in machine learning is motivated as a way to replace this multi-scale approaches that currently exist. And the another aspect is experimental validation, and also to understand what can be seen in experiments and what do we want to predict, so that then we can actually compare it with experiments, correct? So for example, if let's say you train a machine learning model to predict stress, but if you can't really look at stress or measure stress directly, then you are again not in the position to validate them very well, right? So what can we see? We can see deformation. We can use some sort of DIC measurement to get strains. You can also see fractures, right? So if you were to make a prediction on damage, you can actually look at these things in a microscope, and then you can say whether your prediction matches the observed morphology or not. And when you go down to the scale, for example, in this paper by Weitan and Emilio Martinez-Panier, what they show is that you could change the porosity using the simulation tool, and then you can compare with experiments where you again control the microstructure very well and you tested them, and then see whether your high fidelity model is able to predict it or not. Right? So this was another motivation for us to figure out what to predict so that we can actually compare it with reality. And But then, as I said, the challenge is that traditional methods like FEM, if you have to mesh it so finely with each particle in there, too expensive, and multi-scale and micromechanics exist, but deep learning may provide another solution. So that's sort of the background of how we got into this area, I'll probably generally skip this slide. A lot of you are familiar with what data-driven approaches and physics approaches are. In a way, if you have less data and lots of physics, that's the space where pins are exist. But if you have a lot of data and no physics understanding, then you use a purely data-driven surrogate. And then there are things in between. A lot of research has gone into this, including some of the works of Showick that are widely cited in the literature. And when we went through all this literature review and looked at all the various options that exist, we thought maybe you should start with CNNs, test it very well, simple to use, something like a unit model. You can pull it off the shelf, open source codes available. So let's start with something simple, you know that it's going to work. And then we can try the pins, we can try transformers. And we tried transformers and we failed very badly. They were very expensive, didn't work the way they did for fiber composites. But here we are, right? So CNNs were sort of the easiest thing. You know, we can get things working very quickly. And so we started with that. And then I'll show a little bit on pins as I move forward. And then the sort of I wouldn't call you know the sort of you know what the kind of problems that we are trying to solve really here. We want to solve inverse problems because that's where there is a lot of science to be done in a lot of applications. And the goal is always, can we combine data and physics in certain ways so that we can get the benefits of both? So in some cases, you don't know what the governing equations are very well. And so you want to discover those governing equations. So you want to do some, you want to incorporate some data, but you also want it to be constrained by some physics and not just be driven by data. So how do you do that? Is also something that people are looking at, and that also motivated us to pursue some of this research. And so that's sort of the broad background. And with that, we established the 3 research goals for this project, which was funded by 3M. And so we pitched to the company saying that we are going to advance and translate emerging deep learning techniques to simulation of fracture and damage in heterogeneous materials. First, we'll look at these data-driven CNNs, which are hard to train in the sense that you need a lot of data. That means it's just intensive computationally. But then once it's trained, inference time is great, very fast. So that was our first publication, which I'll present immediately after the slide. Then once we had the CNN, can we use that to actually optimize the composite microstructure? In this case, we are going to look at very simple idealized structures and show a proof of concept. So that work was published early last year in this Composites Part A. I'll show a few results from that work. And then I'll get to this physics-informed cell representation, which is almost close to publication. It's going through a minor second review. And there, the idea is, first, we started with damage and flow and diffusion type problems. But then as we were doing these benchmark problems, we realized that they can actually better represent multi-scale features. So I'll touch upon that, and then I'll conclude, and maybe we can have a discussion after that. So objective one, we have this so-called phase field fracture models, phase field damage model. What is that? So a phase field model is based on essentially two equations. One is your equilibrium equation that establishes the stress field in the material when you're applying, let's say you have some kind of a body, there's some second phase fibers in there, like a composite with, with a matrix and fiber domains. And you're applying some displacement or load, your constraints. And then as you're applying that load, it's going to fracture. Damage is going to nucleate at some stress concentrators, and then it's going to develop fracture. The phase field model represents those fractures in a diffuse sense. Instead of saying it's a sharp crack, it's going to spread it out, smear it out. But the governing equations are based on the free energy. Right? So you start with a very nice TD of Griffith's energy formulation. You can write down the contribution from the elastic bulk elastic energy. You can also write the energy from the interface when the fracture is forming, and then you do some manipulations and you get the equilibrium equation and you get the phase field damage equation, which looks like that. So it looks like a diffusion equation with the Laplacian term and some, you can call it a production term or a reaction term. So this is an elliptic equation. That's also an elliptic equation. But if you add a time-dependent term, like a viscosity, you can also make it slightly parabolic. But this is, most of you are familiar with the strain displacement, stress, and so forth. And so you essentially have to solve these two equations. You can solve it in a staggered manner. First, you solve the equilibrium, get the stress field. Then from the stress field, you calculate the so-called crack driving force. And then once you get the crack driving force, you put it into this equation that tells you how the damage grows and where the damage grows. And then when you do this over multiple steps or iterations, then you get fractures forming. Okay, so it's a very well-established method. We published some work on it back in 2021, and we have this model, and we can use that to generate a large data set of how fractures are going to form if you have microstructures where the fibers are randomly distributed. Okay? And our goal was, and I'll come to that in the next slide a little better, is we don't want to do the FEM part all the time because it's time consuming. Can we take a microstructure and pass it through a very fast machine learning model and then predict the outcome without having to do FEM, right? So we want to replace essentially FEM with the CNN model, which is the surrogate. But to do that, it's a data-driven approach. So we have to generate lots and lots of data. So we use Phoenix, an open source code. We wrote that in Python. And then we wrote a code to generate these microstructures where the only thing that we are changing in these microstructures is the centers of it. So we randomly seed the centers, and then we make sure that the fibers are not overlapping and have some distance between them. And then once we do that, that gives us one realization. And we can do that many, many, many times randomly, and we can get 1,000 different microstructures. Fiber radius is the same, material properties are the same. Only thing that is changing is the center of the centroid location of each of those fibers. And so we let's say we generated 1,000 of those, then we have to mesh them. And because the phase field length scale is so small, and we want to You want to capture fractures that go between fibers in these very tiny narrow graph. So imagine how much we have to refine. So take, this is a 50 micron by 50 micron domain. You take a small chunk of it, and then you zoom in. You still cannot see the mesh very well. Then you have to zoom again, and then you're seeing the triangular mesh, right? And the reason why we have to refine that much is because the length scale of has to be that small to make sure it matches with the material properties. Okay? So if you know the fracture toughness, and if you know the critical strength of the material, those two parameters give you an estimate of the length scale. Right? So you have to make sure that the mesh is good enough to resolve that. So this is what makes it so computationally expensive to do this simulation for these kinds of problems. Right? You need a very small mesh size. Okay, so we still have we have parallel computing. We have a very good server, so we could run it in embarrassingly parallel fashion. And once we do each of those simulations, we get a force displacement curve. We can capture that peak load up there. And then we have also at the point where the peak load is, we can get the microstructure, the distribution of damage in the microstructure, like an image, correct? And then we can also get the image of the stress field at this point, okay? And our hypothesis was that the damage or the stress field at the point where there is we have this peak load are somehow a good indicator of what that peak load has to be. Okay, so let me explain what that means in the next slide. Okay, yeah, sure.
Sorry if I missed it, but what is the material model used in any of this? Any plasticity or everything is brittle?
Right now, it's just linear elastic brittle.
Everything.
Yeah, right. Yeah, thank you. Good question. So we have a baseline model. What is a baseline model? So if you are somebody in the field, you want a very fast prediction of, okay, this is my microstructure that I 3D printed. What would its peak load be, right? So you want to take this, put it through some black box CNN model, and you want to predict one scalar, right? So image to scalar. So this type of model is called VG16 type model. You probably know the sort of architecture. Some of you. You take an image, you have some resolution, you go from a high resolution to a low resolution, but more channels and so forth. And then eventually you do all that, you do some flattening, patch normalization, and you get one scalar peak load, right? So if you take this baseline model, the simplest one, and it has been applied in some publications. There's one publication in Computational Material Science Journal that we looked at. And we tried that, and on the training data, you're getting good match. There's maybe a little bit biased, but not too much. And this plot is showing the match between the peak load predicted by machine learning, that baseline model, and also peak load from FEM. And here, these are the 800 training points that we trained it on. Of course, if we trained it on it, it has to do a better match, right? But then the 200 points that we kept for testing, if you make the prediction on it, it's really bad. It's all over the place, right? Honestly, I could have rescaled this and showed that it's better match, because I could have scaled it from 0 to 3000 rather than choosing these bounds that I did. But the point was to show that it's not good, right? So we had to actually show that but using this scale. Clearly, that's not ideal, right? So our hypothesis was that if we informed it, not just with the microstructure image, but with some other intermediate physics information, like damage or stress, it would do better. Okay, so let's test that. So what we said is, instead of passing the microstructure through that, let's do this, where we take the microstructure, we pass it through a unit. A unit, as you know, it has this encoder, decoder type structure. it's an image to image predictor. So we go from microstructure image to damage field image. And remember how in my phase field data, I record the peak load, I record the damage image, I take the FEM data and interpolate that onto a pixel grid, 512 by 512, and I generate these damage images. I use that for training and then testing as well. Okay, so first you go from image to image, and then you use the damage image through that VGG16, and then you make the try to make the prediction for peak load. So you're just, instead of doing it in one step with the baseline, now you're doing a two-step. Okay, how does this do? But before that, maybe just a quick look at how the unit looks. Probably we'll skip this one unless someone is really interested in how we do the various blocks. This is what we get. Okay, so we are only looking at this unit prediction capacity. So out of the, let's say, the test set, which is 200 data points, we have some where it has a good match. We have some where there is match is not so good. So if you take the lowest error case, you're getting maybe less than so around 9% error, right? But the RMSE, the total normalized error is like 4%. But if you take the highest error cases for damage, in some points you get 30% error, right? So it's not the best in terms of getting full field image for these sorts of fracture type problems. So, but what we found out is that even in the worst case scenario, it's getting the right locations of damage. It's just that the magnitude of the damage was not very good. Yeah, please go ahead.
One confusion.
Yeah.
So are you keeping the crack initiation that are not scale invariant in all the simulations, or you are randomizing that?
So in this case, there is no initial crack or notch. So the damage is just nucleating because there are stress concentrators. So this is fiber, and that's matrix.
Okay.
And so because of that mismatch, you get stress concentrations, and that's what is causing these. And you can actually see that whenever the fibers are close to each other, that's where the damage is actually more. So in a way, there is some relationship between fiber distance that is driving these sort of things along with the load that we are applying. And it's a simple uniaxial tension that we are applying.
So
Yeah.
what's the stiffness mismatch? Like what is the difference of the stiffness and the ratio of the stiffness of the fiber and the matrix?
We took the properties of an epoxy matrix and a carbon fiber. So it's quite high, like maybe 2 to 3 orders of magnitude. Yeah. So then the point to take away from this is that even in the case where you have 30% errors and maybe the normalized root mean square error is like 26%, even then it's getting the locations right, the magnitudes are off. So it's very hard for a problem where you have a peak load that goes so high and then immediately drops. It's very hard for these methods to predict, is it 0.3 damage or 0.6 damage, because it's happening so fast. Within one step, it's damaging quite a bit, right? So it's not something that it can learn very easily from these very vast number of microstructures, but still it gets the locations right. Okay, so how does it do with peak load? Because peak load is not a point-by-point information, but rather an aggregate. So maybe it does better. And in fact, what we see is that the same plot, FEM peak load versus machine learning model prediction for the test set, not the training set, for the test set. Previously, we were doing bad with this baseline model, but with the new model, we are getting a little bit better. You can see that these things have, on the same scale, these things have come closer to that 45-degree line. And you can also see that from this model where we see that a lot of the two-stage model ones are in the low relative error, whereas the gray ones corresponding to the baseline are more in the high error cases. But still, this is not something that is groundbreaking or phenomenal. Okay? It's not like a game changer. So that's why it got into a special issue in Journal of Engineering Mechanics. We weren't able to get to JMPS or any other high impact factor journal. But to summarize this was our first curiosity question. Can we do better by informing the machine learning model with not just the microstructure information, but some other physics quantity, either something like damage, and do a better job at predicting? And we say that the two-stage model is more accurate than the baseline. So now the question is, how can we further improve it? And how can a surrogate model guide the design of microstructures, which is what 3M was funding us to do, the inverse design part, not the machine learning. Yeah, please go ahead.
So in the two-stage one, what extra physics did you incorporate?
Yeah, so it's data driven, right? So that means it's not a physics informed machine learning model. But what I'm saying is, so you have an image of the microstructure, and then you're predicting a peak load, as opposed to you're taking the image, predicting some physics-based quantity like damage or stress, and then using that stress to predict the peak load. Right? So that means you're using some physics, and the idea that the nucleation of damage is the one that is governing the peak load, correct? If you think of the mechanics, or the stress at the point when it gets when the peak load drops, that must correlate in some way with the peak load. So that's the physics. So it's physics based or physics guided. I don't know what the terminology is, but
it's a way your characterization of damage is more physics based now, as opposed to what it was.
Yeah, right. So just instead of going purely based on an image of the geometry of the microstructure, you're now informing it with some physical quantity. Yes, yeah. Thanks for that. So then we move to the more interesting part, I hope. The first thing we wanted to do is improve the accuracy, right? The easiest way to, of course, improve the accuracy of a data-driven model is to generate more data, or to do something smart with the data. So what we said is, there is a case to be made that there is a flip equivariance and flip invariance in these cases. That means that, so if you take this microstructure and you flip it, the damage should also flip, technically, right? Because of how it is. And so you can now take one microstructure, flip it, and then flip the image, and then you got another set of the data. And you can do that 2 more times, and then you get 4 times the data. And so that is the equivariance part. But the peak load in all of these cases should be invariant, okay? Because you're averaging it over the entire width, right? So the peak load must be invariant, but the damage field or stress field should be equivariant. We could have done this much smarter and much more mathematically rigorous if we use some kind of like a block to enforce the invariance within that architecture itself, right? But we wanted to do something quick and easy, and so we took the easy route. So now we went from 800 training set to 3200. That means we took our same data set, we didn't do any more simulations, we just flipped them and then got the flipped images, and now we made the 3200 data set, and then now you can train it. More data means better accuracy for the data-driven CLM. So we did that, and then we also said, let's not do damage field, let's do a stress field. And for stress field, you know that if you integrated the stress on a horizontal line, you can calculate the force, and then you divide it by the distance, you get a traction, if you want traction. But you can just directly get the peak load by just integrating along a horizontal, all the stress in the normal direction, in this case sigma yy, and you get the peak load, right? So you don't need another CNN model. In fact, in hindsight, so we did this whole research. Our paper got accepted, and then we were thinking and said, why did we do it that way? We should have done it this way in the first place. And so sometimes that does happen, right? That you get these ideas a little bit too late than when you should. But then we said, okay, let's do the stress field and then just integrate it along the line, and then you get the peak load. And the hypothesis that stress field will give a better indicator for the peak load than the damage field. So how do you do the force calculator? It's an image-to-image model. You give it the image of the microstructure, it predicts the image of the stress field, and then you go pixel by pixel and add all those pixel values, and then you average it over there. You got, or if it's forced, you don't even have to average, you just add them up, right? So in this case, what we found out is a much better alignment when you try to predict with the machine learning model. So in this is the test data. Previously, if you remember, the geometry to damage to strength improved it better than the baseline model, but it was not so spectacular. But now if we did using stress, it was doing a much better job. And after we got this result, it was almost like, duh, this should have been on our minds at the beginning. But I would also say that there is a thing that I'm not clearly delineating here, in the sense that this is the one with the data augmentation and this is without data augmentation. So that data part also helped. And also the using the stress and eliminating the second CNN model also helped. So we were able to make the prediction accuracy go from 2% for the strength or the peak load to 0.6% error, right? So very low error, so to speak. Okay, so I convinced you that informing with some physics and then making this prediction for peak load is better than just going baseline microstructure, complete black box. And now, does it actually work if it's an inverse design framework? Okay, and so what I did was you have the design parameters, but in our case, only the fiber diameter is fiber diameter is fixed. The location is varying. The volume fraction is also fixed, right? So we are not considering all the design parameters. The only design parameters we're changing or allowing it to change is the location. That means move these fibers randomly. So the question we asked is there an optimal pattern of these fibers that gives the maximum peak load? Right? Very simple question, simple microstructure, toy problem. And so what we need is an end-to-end forward model so that when we back propagate automatically with auto differentiation, we can do the inverse calculation. So if given this fiber location, we should have an automatic way of generating the differentiable simulator. This essentially uses sort of a sigmoid function in a way to just say generate like a level set type of figure, right? So we give a sigmoid function such that sigmoid function is 1 if it's in the fiber and 0 if it's outside the fiber. And then you overlap all those sigmoid functions of every little fiber, and then you put it together, you get that total image. Okay, and so this is a differentiable simulator of the microstructure. And then we have the CNN already, and that predicts the strength. And now you're using constrained gradient descent. So it should be gradient ascent, but we take the negative of the cost function, and it becomes gradient descent, and we back propagate. And our aim is to optimize this microstructure. We have the CNN-based model, and then I'll skip through these details in text. And what I'm trying to say here is that it's not just sufficient to only put your optimization as just the peak load, because you also want to account for some losses that avoid certain unphysical behavior. So for example, you cannot have fibers overlapping. That's not physical, right? So that means it's not just sufficient to just say, I want to maximize the peak load. You have to put some constraints on it that fibers cannot overlap. And because we are trying to keep the volume fraction constant for these sort of simulations, we also have to say that these fibers cannot leave the domain. So that means that at the boundaries, there has to be some penalty, which is called boundary intersection loss, so that when it's going close to the boundary, it pushes it back in. We could have done that periodic type stuff where it leaves from one side but enters from the other side, but it was a lot more complicated to do that in Phoenix. And in fact, in original Phoenix, you can't even apply periodic boundary conditions. You have to go to Phoenix X perhaps. So we took the simple way out, just let the fibers not leave the domain. And so this is a simulation for when I'm trying to optimize the peak load in the Y direction, right? And so I have the peak load in Y as my optimizing. I have the fiber overlap loss and the boundary intersection loss to make sure the fibers don't leave. And as you can see, it starts from some low random initialization, which starts at like 3000 peak load. And as the locations of these fibers are optimized, it goes to 4000, bounces around a little bit as it's trying to move things around, and then it converges to a type of shape, which you probably notice is called the hexagonal close packing, right? Or right, so you have one fiber surrounded by 6 fibers, like the hexagon. And the interesting thing I would say is we didn't expect this, that the peak load that it was predicting with this optimized structure was 4000 when our training data set was only between 2900 and 3600. That means that it was going out of the training regime. So sometimes people will say, oh, CNNs, machine learning, they're only interpolatory. They don't have the capability to extrapolate. But if they are somehow based on physics, I think that it's okay to say that in this case, they are learning something and not just being an interpolator, right? And the other thing I would say is all the training data that we provided are randomized locations, but it's giving you a structured system. We never had a single structured initialization in our training set, but it still was predicting a structured system. So that means it's learning something to optimize the distance between it. And then we took the final one, the microstructure, and we meshed it, and then we calculated with FEM, and we got less than 2% error. That means it's actually making a good prediction compared to FEM. So now we said, okay, now we want to optimize only previously in only Y. Now let's do it both in X and Y. Right? That means that still uniaxial tension, but we want the same tension in both directions as opposed to one direction, right? And when we do that, now you don't get that same hexagon type structure. In fact, what you get is a type of what we call a diamond pattern. So that means that 4 fibers form like a diamond-like structure. Okay, so you don't get like 1 fiber surrounded by 6 in a way. And the same thing goes from a low random initialization to something. In this case, now you don't get the 4000, you get the maximum peak loads at 3800, but they're equal in both directions. Whereas in the other case, you're getting 4000 in one direction, 3600 in another direction. That means when you try to optimize in both directions, there is a cost to pay. The large direction comes down, the Y direction comes down, X direction goes up. And similar pattern that it falls out of the training regime. That means it's still learning something. And then when you predict it with FEM, you get almost like 2% error in both X direction and Y direction strength. And in fact, if you look at the literature, you do have these structures, right? This is the diamond fiber arrangement, which is what we were getting for when you optimize both in X and Y. If you optimize only in the Y direction, then you get the hexagonal type pattern. So we were encouraged by this, but nobody will ever do something so complex and get this, which is already well known, right? So what was the point of it? You could ask. And so we don't know, because we started with curiosity. Sometimes that's the downside of doing something just based on curiosity and not based on like outcome. But we thought through it and we said that maybe in the case when there is some sort of a notch or a fracture or something in the part, can we use the fiber arrangement so that you reduce the volume fraction of these fibers, but place them optimally in fewer numbers, but without drastic reduction in the fracture toughness. So here I'm showing sort of that concept where, let's say you have a notch, you could put 50% fiber into that microstructure, right? And then you get a peak load of 520 units. But if you use smartly lesser and lesser fibers, that means here I'm only using 25% and 12.5%, then I could place the fiber such that the fracture toughness of this microstructure, even with 1/4 of the fiber volume fraction in the original case, does not have that much reduction. So that's what I'm trying to say. For the optimized microstructure, reducing the volume fraction to 1/4 only causes about 10% decrease in the strength. That means you dropped it by a lot, but you still retain a lot of the tensile strength. That's because, of course, if you take a very stiff fiber and place it at the fracture tip, that's going to arrest the crack and make the crack path tortuous, and it's going to increase your fracture toughness, correct? So it seems to capture that. It seems to show us that these kinds of optimal placements are viable for complex domains, complex geometries, and so forth. So that's where we could probably use it. To summarize, and I don't know if I'm running over time, I'll try to maybe speed up the next part. So in this, I was able to show that, yes, we can actually make this inverse design and probably use it in cases where you need to reduce the use of fibers by reducing the volume fraction, but still keep retaining very high peak loads, right? Now, all this was CNNs. We then asked the question, can we do all this with pins? Then we don't have to generate so much training data, and we can just use our phase field PDEs as our loss function, and can we not do it? So that's the question. And when we tried that, we found that it was much, much more expensive than running a FEM simulation. And we went down this path with my collaborator, Matt Berger, if you can use a grid-based representation to make the performance of pins faster. So I'll quickly describe that in the next maybe 10 minutes. And a part of the motivation was also to use those kinds of grid-based methods to solve flow laws. So if you have Antarctic ice sheet, you have to solve these Stokes-like equations, PDEs. And so you can actually use a pin to solve these, okay? And this is a paper that was published in Science by one of my collaborators through our NASA project. I'm not a co-author on this, but Yalba is my co-PI on the NASA project. And so that was part of our motivation. We now have a foundation project from Ising-Simons Foundation, where we are again looking at ice sheet models, where we go from velocity to stress, and then we add some pressure. And then right now we are using a phase field fracture model to predict how cracks are growing in the ice. But our grant wants us, or our grant aims to replace that phase field with a neural network surrogate, right? And this is where I need help of brilliant minds like Shavik and others, right? Because I can't do it myself. So what we want is we take this input, put it into a neural network that's well trained, and that gives us how the crack depth is. But what we also wanted is a physics-informed neural net that would be much faster than the traditional pin. So we looked into the literature, into this coordinate-based one. So in these models, what you do is you have a domain, and you give input as x, then the neural network has some function that takes in x. It has some parameters of the model, and then using that you can do auto differentiation, get the derivatives, and the derivatives go into the loss function, and then you optimize for the loss function. So you probably all of you know that. But if if you have to do the boundary aspects, because the PD is only defined in the domain, outside on the interface you have boundary conditions, you do the same thing. You sample on the boundaries, and that goes into a PDE loss function, and then you add the boundary loss with the interior loss, and you have to use some weighting factors to make sure which ones you want to put more and which ones you want to do less. So there are some downsides to doing that. That really degrades the optimization when you do these sort of things. So we learned and noticed all that. And then we also looked at these strong forms which have second order derivatives. But if you actually consider variational forms, in fact, I think Shovik and Somadutta Goswami kind of proposed this energy form loss, one of the first one or two people to do these sorts of things. And so we also liked that part, that we don't want to use the second derivatives, we want to work with first derivatives with the variational form, bringing in some of the FEM aspects. So this is how the model works, right? So we don't go from X with the MLPs directly. What we do is we have multiple grids, like a multi-grid method. And the idea comes from this paper by Miller et al., where they use this for graphics applications. They call it the instant neural graphics primitives for multi-resolution hash encoding. So if you have a figure, you want to make that figure a high resolution description, but with low requirements in terms of memory and stuff, then use the sort of multi-grid cell-based representations. That was, I think, the idea. So here, the big broad idea is that we take X on the grid, right? And at each of those grid points, you have grid parameters, which are like these feature vectors, and use those grid feature vectors to interpolate what is a feature vector at that point. You can use something like, bilinear interpolation, finite differences, and then you push that into then an MLP, right? You do the interpolation, you push that into MLP, and then you predict that field that you want to predict, right? And so that means, what are we doing? This is sort of like that two-stage approach. Instead of directly going from X MLP to prediction of the field, you're now going X, go to the grid, interpolate onto the point, the sample point, and then push that interpolated feature vector into an MLP, and then you're making a prediction of the field, and then you're optimizing that loss function for it. So I'll skip some of these decoupled training and stuff that we do for handling boundary conditions and all that. It's not that relevant to what point I want to make in the interest of time. And we said, so we have this, and we first started actually, so let me go a few slides back. We first started with phase field damage because that was our motivation. And when we did that, we weren't getting very good error losses. That means if you take the standard pin, it starts with a very high error, and then it drops within a few time steps of training. Whereas if you take the grid-based method, it starts with a low error, but still it wasn't going below 10 to the negative 2. That means we're still stuck with like maybe 1% error or less, right? It's not performing as well as we wanted it. And honestly, like a lot of it was flat. It was not going down steeply. And so, for the phase field, we didn't find very good behavior. So we said, why don't we actually look at what it's good at? And what we found out that it's good at describing things where there are multi-scale features. So let's say you're solving a problem where you have a permeability field that has high frequency oscillations, right? Then you have sinusoidal functions. In those cases, the pin was struggling a lot, where if you take the standard pin, your errors are struck at 10%, right? But whereas if you, for those kinds of problems with multi-scale features, you couple the ability of the grid to represent these smaller scale features well, and then you're optimizing it over that, then you can see that we were getting to errors below 10 to the negative 3. And we were getting much wider loss landscapes than just like only initial drop, right? And same thing, we also tried to do this in heterogeneous media where it's not just the permeability, but also some other force functions that had high frequency features. And we also saw the same thing, that the standard pins were not doing so well. You get orders of magnitude reduction in error in the cell-based ones. But the downside of what we did was that we are restricted to rectangular grids. And as you know, most mechanics problems are not rectangles, right? You have to have complex geometries. So, and because we use the bilinear interpolation, finite differences approximation, we are restricted to these uniform rectangular grids. So that's sort of a very, very strong limitation, maybe the Achilles heel of these method that we realized. But that's where we stop. We have summary, we have more examples in the paper that soon will be published. Hopefully it'll be in the next month or so. I'll share it with Shoaik if anyone's interested. I'll conclude by saying a few things. So in the first part, we did the UNet, works better than the VG16 type model. Data augmentation was useful. Stress-based force calculation improved accuracy. Then we could use that in inverse designs. We showed some simple hexagonal diamond arrangements that come out of this optimization. And then finally, we had this bilinear interpolation grid-based multi-layer perceptron MLP. And when you use those cell-based MLPs, they were not very good for phase field type problems, but they seem to be better for these multi-scale elliptic PDEs. So sometimes you start with something, you end up with something that you don't know. So that's how research works. And in future, we want to do these, we want to overcome the limitation. That means instead of the rectangular grids, what if we had a finite element grid and we use finite element interpolation, not the finite difference interpolation, and then we can use the same MLP based prediction, right? So, and we looked into the literature, and one of my friends, Kai-Chi He, has already proposed that. So now we are trying to use these neural integrated meshless methods, and we are trying to use that for ice simulations, maybe use for inverse estimation, robust Bayesian inference, and then we want to apply it to maybe Himalayan glaciers. Shoaik and I have been talking about it. It would be helpful for hazard prediction or maybe hydrological modeling and planning. And then finally, we also want to apply it for fracture and calving and create this neural calving ice sheet model. We call it NewSyn. Yeah, so we want to, we have lots of ideas and very little time. So thank you all for your attention, and I'll be happy to take some questions.
Then you can have some questions. Questions, if there is some.
How bilinear interpolation is helping?
Yeah, so in the way that we are implementing, so think of an MLP like this, right? So you're applying it on the whole domain, and I'm probably giving a very layman kind of explanation. Shavik, maybe you can help me with more mathematical here. But so let's say you have a very complex, high frequency type solution that you have to represent. An MLP would need to represent all those things with the parameters of the model, just the parameters of the model. So that means you probably need a very deep network, maybe a very wide network, and so forth, right? So, but whereas if you use the grid, what happens is some of the parameters of the MLP now are now replaced by the grid parameters. And so what you're doing is you're now defining the model parameters at the grids as grid-based unknowns, like in a FEM, right? Like your unknowns of the displacement in FEM are defined at the nodes of the finite element mesh. So in the same way, your feature vectors, which are those parameters, are defined on these grids. And that means that we don't need a very deep network. In fact, we are using one hidden layer, a very shallow network. And what bilinear interpolation does is that it is very fast, and we used CUDA subroutines to do that, tiny CUDA library. So it was doing it much faster than your Python PyTorch modules. So we got acceleration from that as well. And majority of the acceleration came from the fact that we were using a very shallow MLP, right? So instead of using large number of parameters to describe the entire landscape, you break it down, and your MLP is only trying to represent in smaller regions where the nonlinearity is not so high. And so then you don't need a very large or deep network. And all that put together makes it computationally very good. In fact, in some of the work that I've shown, if FEM took maybe, I'm making up some numbers, 50 seconds, our MLP-based method was only taking 150 seconds. So that means it was only 3 times more expensive, which is very good for a standard pin if you do a forward simulation, right? FEM is still very fast for some of these problems. You cannot beat it. But we were still getting close to that time, and not like 10 times the time or 20 times, right? So that's how it helps. Hope that convinces you. Yeah, please. Yeah, go ahead.
Yeah, so you are talking about multi-resolution grid, like here, multi-scales are there. Like, how do we decide like how many resolutions we need to take and where the grid point we need to take? Because I think very problem specific.
Yes.
Right now. We don't know where to put that thing to get the better result.
100%. So that's the hyperparameter study, right? Yeah. So what happens is how many levels of grids you use. So in one case, we did 2 levels, 4 levels, 8 levels, and 16 levels, right? That means we take something which has 2, 4, 8, 16, and then keep resolving it like that. So that's one type of hyperparameter. The second type of hyperparameter is how many feature vectors at each node do you define, and so there are a few hyperparameters like that. And so you have to do a study, and you have to figure out which one is optimal. And what we figured out is that somewhere around 4 levels to 8 levels is optimal for the problems that we studied. And beyond that, you don't get much benefit from the levels, if I'm not wrong about with my memory. But we did an extensive hyperparameter study and showed all those things, like how do you choose the architecture of this grid-based MLP so that you get optimal performance in terms of error, landscape, and time.
So for a complex problem, this will be increased a lot, and the computation time will also increase in that scenario.
Yeah, but the idea is maybe once you figure it out, then solving similar problems like that with only like a minor coefficient change or something would be faster. right? Eventually, that's sort of the goal, right? Like going from a pin to like a PINO, which is a physics-informed neural operator, where the PDE itself has some unknowns like parameters and stuff that we don't want to keep retraining it. But you're right in the sense that right now the way it is, it's just a pin, so it has all the limitations of the pin.
Yeah, very nice talk, first of all.
Yeah.
I should have maybe remember the slide number, but you showed this picture where you had your domain, but you reflected it across X and Y axes, and then you had 4 times the data,
Yeah.
and then you got better results.
Yeah.
Right. I'm very surprised for many reasons. But I will state just one here because there are too many. And that one is that just do it once more. I mean, you keep doing it, right? Now you have these 4, then you can further have like 16, 32. Why just stop at 4?
Yeah, I mean, I have to think about why there would be more than 4 flips, because I'm thinking in terms of symmetry of the problem.
No, so now you
Right?
have a greater thing, right? You just flip that across X and Y axis again. So now you will have 16.
Oh, you're saying that I could combine those into one structure and then flip that one?
Yes.
Perhaps, but we are only looking at 50 micron by 50 micron domains, right? We are not trying to increase the size of this so-called RVE. So within that RVE, if I take one image, I could take the flip or another flip and another flip. If I do one more flip, I get back my original one, right? So that's how we looked at it, and we did it 4 times. Now, if there is a way to actually do bigger domains by overlapping stuff and joining and creating more, that would be interesting, but we were happy with the 0.6% error in the peak load prediction, and we stopped. The simple answer is that we had the target set at getting the inverse design working. But
So like
I should think about that more. Yeah.
And also in mechanics, such symmetries are generally encoded in the form of either like principle of isotropy of space, which we also call objectivity,
Correct.
or some kind of material isotropy. How should I think of this symmetry as?
So here, I would say it's just the fact that if I take a mirror image of my damage field, microstructure, the mirror image of the damage field of the stress field should give me the stress field of that, right? So maybe principle of parity is the argument that I can think of. Perhaps it's related. The best way to do it is not through data augmentation, but you should be able to figure out the network itself such that it's already encoded in it, right? And that would be the best way to do it. But yeah, I would say it's principle of parity, right? In the sense that if I'm looking at the microstructure from this side of the system and you're looking at it from that side, right? The left and right should not determine how the damage field should be, right? Like, or should have equivariance.
No, I absolutely agree. But generally, we take care of these things like in the first step in mechanics. So when we build theories, for example, the dependence on the deformation gradient is not through the deformation gradient, but this quantity called F transpose F, which is the right Cauchy Green test. So such objectivities or invariances are built in through the kinematic variables we choose to represent our theories.
So that's there in the physics model, right? So when we do the phase field solution, our FEM does that. So we don't need to flip and rerun the FEM because we know that it's going to come out of it. But the data-driven CNN doesn't know all that. So either you inform it with layers, and I think Jan LeCun has something where he has
equivariant neural network.
Yeah, so he has something. So that was our idea, but then he said, okay, we want to do something quick first because we had this paper as a special issue, and the deadline was like in a few months. So we took the easy way out and just did the data augmentation. Yeah, but the CNN doesn't know unless you tell it. Yeah. Yeah, great question. Yeah.
Hi. So thank you for the great talk. I just need to know this that you are combining these 4 features at that X location, right? So are these like being combined using some formula, or can we make that learnable as well?
Yeah. So in a way,
So that
In fact, this-
maybe graph type of learning, right? This is possible.
sure. If you interpret this as a graph, perhaps, but I would be speaking out of my comfort zone if I hadn't had answered about graphs in this, because I don't know much. But here, what I would add is that the size of this feature vector is also a hyperparameter. That means that what I'm saying here is that there is a feature vector here which has 4 values vector, right? I could make it 8, I could make it 16 or whatever. And that would be the one then pass through it. So it's a hyperparameter, and we've generally found, I think, 2 or 4 is good enough as the feature vector at the nodes. And we take at each point think of it as FEM. Think about it as FEM, right? Like, so you have 4 degrees of freedom at each node. I think of it that way. And then you're interpolating that to get a 4 degree of freedom feature vector at this sample point. And then that is the one here, and it's getting passed through the MLP, right? So that we could make it 8, we could make it 16, or we could make it 2.
So right now, we can play around with it, right? Make it learnable, make it maybe.
We could, yeah. And I don't know what that type of thing is called, multitask learning, or I don't know the terms for
There is a relation.
meta learning, right? Maybe. Yeah. So there is a term for that, where you learn the hyperparameters of of your implementation itself, and then you use those optimal hyperparameters.
And one more small thing,
Yeah.
I may have misheard that. So maybe once or twice you said that train was slower than FEM.
That was including training, right? Including training time.
Yeah,
So,
including.
yeah, so it is not about inference, right? So
Yeah,
it includes
yeah,
training.
yeah.
That too is obvious.
And in the initial part, in the very first thing that you did, where you had 2 models, one was autoencoder or encoder
Yeah,
decoder,
yeah.
and then there was that final model for that post, right? So in that, the training was end to end, or the first part was trained separately and then the second part was trained?
Yeah, that's a good question. We did it separately.
Oh, you did it.
Yeah, we
But
said-
did you check maybe?
I think we did, but because our errors were good enough, we didn't bother to do it. But you're right in the sense that we could have trained both of the parameters of it together.
Yeah, end to end.
In fact, what we could have done is taken the unit, dropped the decoder part, and only taken the encoder part, and directly tried to see if we can jointly predict the peak load at the same time as we predicted the stress. Correct? So we tried that too, but I think eventually we ended up with this as the good approach. And my student can tell more about his actual experience. Yeah, thank you.
Okay, so if there is no other question, oh, you speak, right?
So hi, so in the inverse design world, so the differentiable simulator is doing the FM simulation, right?
So no, the differential simulator is taking the design parameters, in this case, just the location of the fibers, and then it's generating the image of the microstructure. And then the image goes into the CNN, because we made the CNN a surrogate for the FEM phase field fracture. We never have to do the FEM. And that's why what you're seeing in some of these simulations, right, like where it's getting optimized very fast. These ones that I showed, right? These were very fast simulations. You couldn't have done this type of optimization where, let's say, if you had to do this with FEM, you perturb it and run a full FEM model, then you have to take the gradient, right? Like, and then you have to do that. It's not possible for predicting the peak load and then optimizing it with FEM. Whereas
First you train the CNN surrogate with the FM simulation based microstructure.
so first we do an offline training, right? So you have the CNN, where you give it the image, you
Get
make
that.
sure that it's predicting the correct precode. Once you have it, then, once you have it, then in this, where did that go? Yeah, this one. So yeah, in this one, there is no FEM now. Once you generate the image, you just pass it through the CNN inference, and then you get the peak strength very fast, orders of magnitude fast. And that's the benefit of a data-driven model, that at inference time, it's just negligible, the cost. And that's why we could do these simulations very fast and get these kind of optimizations.
Okay.
Sure. Yeah.
So let us thank the speaker once again.
Great talk.
For the students, I have kept one interaction session. If you are interested, I've sent an email. You can sign up for that, which is tomorrow 4 to 5, I think, if I'm not wrong, in the library.
Yeah.
On the other side. Okay. And yeah, thank you. And yeah, great talk.
Thank you. Thanks, everyone.